Okay, so we're going to be looking at the present and future values of a continuous income stream and how we can use integrals to model this. So if we recall, we have this equation, f is equal to p times e to the rt, where p is the present value. This is for one particular investment, so I take p dollars and I invest it at an interest rate of r. R is the interest rate for t years. T is usually the time in its usually years. And then I get f is the future value. So the idea is that this is for one particular investment. I take p dollars, I invest it at an interest rate of r, continuously compounded. That's why it's this e to the rt thing, and not like 1 plus r to the power of t or something like that. It's continuously compounded interest. I should probably write that in. This is continuously compounded. And I do that for t years, and I end up with f, the future value. So that's the value of the thing when the investment matures. And we're going to be using this to see how we can come up with an integral that tells me that if I have an income stream, s of t is an income stream. So at any time t, money comes in from this income stream. Maybe it's revenue from a business or something. The money comes in, and then I immediately invest it as it comes in, each new bit of money, at a rate of r. And I invest it not for a particular, not for a particular period of time, but how do I determine what that particular, that amount of time is? It's going to depend on when the money came in. That's the issue. So we have, that's our maturity time, m. This is the end, and we're going to call the start 0. And the idea is that as t goes in between 0 and m, I get, so this is some point t in between 0 and m, I get s of t dollars comes in, and I invest it at this rate r. And how long do I invest it for? It's going to be m minus t years, again, usually measured in years. And so the idea is that as t goes from 0 to m, can I figure out how much of this, how much money I make in total? And so the way I'm going to do that is with an integral. I'm going to partition this interval from 0 to m. So I'm going to get here, this is t1, and that's t2, and I keep going like this, ti, and ti plus 1, all the way to the last one is going to be tn, and that's like tn minus 1 is the second last point. And the way that I'm going to do this is I'm going to think, okay, if I take on each interval, so t0 is 0, each one of these intervals, I think, can I come up with a formula for how much money I make by investing however much money came in on that interval for this amount of time that's remaining until maturity? So the idea is that I'm going to take in each interval, this is the ith interval, I'm going to take a sample point, so any point in the interval, and I'm going to say, well, this is how much money came in at this sample point, s of ti, and if those intervals are extremely small, because to get this integral we're going to take the limit as the length of the intervals goes to 0, well, there wasn't that much time for the income stream to change, so I can approximate. I can say that I got approximately delta t times s of ti star, money in there, and delta t, of course, is the length of the interval. It's ti plus 1 minus ti, the second endpoint minus the first endpoint. So that's the amount of money that comes in on each one, and then I invest it at this rate of r for m minus ti star years, or whatever this is. And I'm going to see if I can figure out a way to add all of these up and find out how much money I made. And then when we take the limit, as we always do with integrals, the limit as delta t goes to 0, so as the partition gets smaller and smaller, this is a smaller partition one, and that's even smaller, as it goes to 0, so that's delta t, and that's the delta t, it's going to 0, it's getting smaller and smaller. I'm going to see, can we come up with a formula that tells me, in terms of an integral, how much money we made? And so the way to think about this is I'm going to say, okay, on my first interval here, I got S of t1 star, my first sample point, times delta t, times e to the power of r times m minus t1 star. And I keep going with this up to, this is the ith one, and then the last one is going to be S of tn star, my sample point in here, times delta t times, let me move it down so I have a bit of space. Actually, I'll move it up so I have a bit of space, times e to the r times m minus tn star. And so I'm adding up all of these, and what am I going to get? Let me bring it down here so it's a bit clearer. I get the first one, and then I get the second one, S of t2. If this is the t2 star, it's in here. S of t2 star times delta t times e to the r, m minus t2 star, plus all the way through the ith one is S of ti star times delta t. And we're assuming the delta t's are all the same, right? They don't have to be, strictly speaking, but we'll have divided the thing up into equally sized intervals. And so this is S of ti star times delta t times e to the r m minus ti star, all the way to the last one, which is S of tn star delta t e to the r times m minus tn star. And this is my sum. And so in order to turn it into an integral, I'm going to see if I can simplify it a bit. The first thing I'm going to do is look at the exponents of the e. So each one of these, I can actually distribute that r in. I can make this e to the r m minus r t1 star. I can make this e to the r m minus r t2 star. I can distribute all the way through. This is e to the rm minus r ti star. And then the last one, after I'll move it over and get even a bit more space, this is getting kind of cramped. The last one is going to be e to the rm minus rtn star. And then I'm going to remember my exponent rules. Subtracting or adding in the exponents is like multiplying the bases, right? I know that a to the power of b times a to the power of c is a to the power of b plus c, whether b or c are positive or negative. So I can simplify this yet again, and to save some space, I'm just going to forget about the t2. You get the idea what's going on there with t1 through ti, the general sort of middle term, all the way through to tn. I can write this as, and this is why I need the space, e to the rm times e to the negative rt1 star. And I can write this as e to the rm times e to the negative rti star for any general term I, all the way through the last one, gives me e to the rm times e to the negative rtn star. And then I can simplify it some more, and notice I have a factor of e to the rm here. All of them have a factor of e to the rm. So I can write this, I can factor that out, say this is e to the rm times s of t1 star, delta t, e to the negative, and I may as well, actually I'll do that in the next step, e to the negative rti star, all the way through s of tn star, delta t, times e to the negative rtn star. And then I can switch around, because I'm multiplying, it doesn't matter what order, I can switch around the delta t, and, whoa, didn't mean to do that, delta t and the e to the negative r times ti, or whatever it is, t1, tn star, e times negative r, to the power of negative r times the sample point. I can write this as e to the rm times s of t1 star e to the negative r t1 star delta t plus all the way through s of tn star e to the negative r tn star delta t. And now I'm in the position to say, okay, what happens when I take the limit as delta t goes to 0 of this stuff? Well, this is like a Riemann sum, right? That's the delta t's times the function. The function is s of t times e to the negative rt. The limit as delta t goes to 0 gives me the integral from 0 to m, because those are the endpoints of the interval that I'm integrating over, of s of t e to the negative rt dt. The dt is the limiting value. It's the infinitesimal of t when I take the limit as delta t goes to 0. So the amount of money, the total amount of money that we made off of this investment is e to the rm times this integral. It's e to the rm times integral from 0 to m of s of t e to the negative rt dt. And what's that? That's the future value of the investment. That's how much I made in total over the period, investing s of t, an income stream of s of t dollars from 0 to m, from the beginning to the maturity m. But we have this equation, f is equal to p times e to the r t. So the present value of this thing is going to be this. That's the present value of the investment. So I get now future value is e to the rm times 0 to m integral from 0 to m of s of t e to the negative rt dt, or the present value is the future value times e to the negative rm. So if I want to find, this is what I use to find either the present value or the future value, depending on which one I have. They could give me the present value and I have to find the future value, or vice versa. So let's do a quick example. If I have an income stream, the simplest ones of these are constant income streams. And S of t, say I get $1,000. At every point t, I'm getting $1,000 coming in. And I have a rate of, say, 0.2, something like this. And my time to maturity, my period over which I'm getting the interest, the continuously compounded interest is 7 years, say. Can I find the future value? Can I find the present value? Well, I have the future value. The f is going to be, well, first of all, what's my m? I have my r is 0.2, which is 2 over 10. Usually it's easy to use fractions. My m is 7, so I'm going to be multiplying e to the rm, which is 2 over 10 times 7, times the integral from 0 to 7, 0 to m, of s of t, which is 1,000, times e to the negative r, which is 2 over 10, t, dt. So this is e to the, I can cancel the 2 and the 10, it becomes 1 over 5. It's going to be e to the 7 over 5 times the integral from 0 to 7 of 1,000 e to the negative 2 over 10 t dt. I can move constants out front of integrals. They're linear. So I can write this as 1,000 e to the 7 over 5, that's my constant, times the integral. I don't know why I can't draw a nice integral sign today. 0 to 7 e to the negative 2 over 10 t dt. And so now all I have to do is evaluate this integral. And how do I do this? Well, first I can simplify the 2 over 10. I can make this a 1 over 5. And this is a u substitution thing, right? And there's a t in there. I can say u is negative 1 over 5t, du dt is negative 1 over 5. So du is negative 1 over 5 dt. And I can write integral the antiderivative, e to the 1 over 5t dt, as equal to, I can solve for the dt if I want. dt is negative 5 du. So this is negative 5 indefinite integral of e to the u du, or negative 5 integral, or just negative 5 e to the u, because e is its own derivative, so it's its own antiderivative, plus a constant. Since we're doing a definite integral, the constants are going to cancel, so I don't have to worry about that. I can just unsubstitute the u, put back in the negative 1 over 5t, so this is negative 5 e to the negative 1 over 5t. And so this is what now I'm going to evaluate, because it's a definite integral from 0 to 7. The fundamental theorem of calculus, part 2, tells me that this is the antiderivative evaluated from 0 to 7, which means I plug in 7, and then I plug in 0 and I subtract. So this is negative 5 e to the negative 1 over 5 times 7 minus negative 5 e to the negative 1 over 5 times 0, which is negative 5 e to the negative 7 over 5 plus, well, it's going to be 5 times e to the 0. Anything to the power of 0 is 1. So this is just going to be 5, which is 5 times e to the 0, 5 times 1, minus 5 e to the negative 7 over 5, or 5 times 1 minus e to the negative 7 over 5. The bracket goes down here. So that's the integral. But I also had this constant that I forgot about, and I have to bring back in, that was getting multiplied by it to get the future value. And I should bring that down, not lose it here. So the future value is this times this integral, and actually, or this, so this is now the evaluated integral. It actually might be simpler to keep it in this form, I'm seeing. This is going to be 5,000 e to the 7 over 5 minus, it's going to be 5,000, and then I have an e to the 7 over 5 times e to the negative 7 over 5, and again I'm going to use my exponent rules. Add the negative 7 over 5 and the 7 over 5, and it's negative 5,000, minus 5,000 e to the 0, which again is 1, so this is going to become 5,000 after I factor out the 5,000, e to the 7 over 5 minus 1. And this is my future value. This is my future value. If I had this, and this is a number, right? This is a number. If I wanted the present value of that number with the r is equal to 0.2 and the m is equal to 7, the present value is going to be that integral that I used to get the future value, that I multiplied the e to the 7 over 5 by to get that future value. The present value is going to be this integral from 0 to 7 of 1,000 e to the negative 2 over 10 t dt.